Chapter 12, Elementary Chemical Kinetics, Section 12.3, Rate Laws and Integrated Rate Laws. We will study the rate laws and the integrated rate laws for the zeroth, first, and second order elementary reactions in this section. For the zeroth reaction, the reaction rate is a constant. From A to P, if it's a zeroth order reaction, the reaction rate R is equal to the rate constant K multiplied by A to the power of 0. Therefore, it's called a zeroth order. And really, R is equal to K. K is the reaction rate constant. It's also known as reaction rate coefficient. For the first order reaction, the reaction rate is proportional to the concentration of the reactant to the power of 1. So from A to P, if it's a first order reaction, R is K times A to the power of 1. Now if we have 2A to P, if it's second order, then the reaction rate is proportional to the concentration of the reactant to the power of 2. The reaction rate is the rate constant K times A to the power of 2, and thus second order. We have another type of second order reactions from A plus B to P. It is possible for the reaction rate to be proportional to A to the power of 1 and also to B to the power of 1. Written in this equation, R is K times the concentration of A times the concentration of B. The reaction order is 1 with respect to A, it's 1 with respect to B, but overall the reaction is second order. 1 plus 1 is 2. Third order elementary reactions are extremely slow because the chance of 3 reactant molecules colliding at the same position and with the right angles of collision is slim. The unit of the reaction rate R is always the unit of concentration divided by the unit of time, because R is how fast the concentration of reactants or products change with time. We often use molar per second for the units of the reaction rate. The unit of rate constant K, however, may vary. In general, the unit of K, the rate constant, is molar to the power of 1 minus n divided by second. And n is the overall reaction order. So if n is 0, we have a zeroth order reaction, and then the unit of K is just molar per second, the same as the reaction rate R. If we have a first order reaction, n is 1, the unit of K is simply second to the power of negative 1. When n is 2, the unit of K is m to the power of negative 1, second to the power of negative 1. Well, this is just because K is equal to the reaction rate over the reactant to the power of n for nth order reaction. This results in the unit of K being molar to the power of 1 minus n, second to the power of negative 1. So we tabulate the unit of R and unit of K for the zeroth, first, and second order reactions. If we look at the unit of R, it's always molar per second. This is just how fast the concentrations of the reactants or products change with time. So they have just the same constant unit as concentration over time. What about the unit of K? Well, again, the unit of K really depends on this reaction order. If it's zeroth order, R equals K. If it's the first order, R equals K times concentration of A. Therefore, we have the unit of K as second to the power of -1. Now in this case, for the second order, R is K times A squared, and therefore R and K should differ by A squared. The units differ by m to the power of 2. Same here for the second type of second order reaction from A plus B to P. R is K times the concentration of A, and then times the concentration of B. And therefore, the unit of K should be molar to the power of -1, second to the power of -1. What if you have a third order reaction, such as 3A to P, 2A plus B to P, or A plus B plus C to P? This kind of elementary reactions, the unit of K is molar to the power of -2, second power to the power of -1. We just use the same formula over here. Fourth order reactions, well, molar to the power of -3, second to the power of -1. Honestly, I have never seen any fourth order reactions myself, including textbooks or scientific papers. Given the reaction rate R at various concentrations of the reactants, we can determine the order of the reaction rate with respect to each reactant. For example, if a reaction involves two reactants denoted by A and B, we may simply just assume R is K to the power of A to the power of alpha, B to the power of beta. Alpha and beta are the orders of the reaction with respect to A and B. And we can determine the values of alpha and beta. If you have an elementary reaction, alpha and beta are simply the coefficients in front of A and B in a balanced chemical reaction. But if you have a complex reaction mechanism, alpha and beta are not necessarily the coefficients of A and B. Alpha and beta are not necessarily integers. And sometimes we can even have a different form than this. So R is a more complex function of the concentrations of alpha and beta. But now let's just assume this equation is sufficient to describe the mechanisms, and then we can just take the natural logarithm of this equation. We get the natural logarithm of R is equal to logarithm of K plus alpha times the logarithm of A plus beta times the logarithm of B. If B is held constant, then we have L and R versus L and A graph with a slope of alpha. So again, if B is constant, we can view L and K plus beta L and B, these two together, as the intercept. When we plot L and R versus L and A, the alpha is simply the slope. Now what if we hold A constant? Now L and K plus A L and A, these two terms together are considered the intercept of the L and R versus L and B plot, and beta is the slope. Well, we can also just determine alpha and beta without plotting L and R versus L and A or L and R versus L and B. Well, it's simply because if B is held constant, if we have the value of the reaction rate at two different concentrations of A, we can do this. Alpha is the change of L and A over the change of L and A. On top it's L and R. Well, why is this? If you look at this, basically it's the slope of L and R versus L and A. And then we just plug in the values what's the change of ln(r), what's the change of ln(a). The change of ln(r) is ln(r2) over r1. The change of a is ln(a2) minus divided by a1. So we have this. Again, if we hold b constant and can measure the reaction rate for two different concentrations of A, and then we can plug in these four values to get alpha. For example, if the reaction rate doubles, when A doubles, we simply have this equal to 2, this equal to 2, the alpha is just 1. Alright, so two different ways. One is you can just plot ln(r) versus ln(a). You determine the slope is alpha. Or you can just do algebraic operations like this. You will determine alpha by hand. Again, if there are two reactants, we can just assume the reaction rate is often k times a to the power of alpha, b to the power of beta. And we take the natural logarithms of both sides. We get ln(r) equals ln(k) plus alpha ln(a) plus beta ln(b). Now if a is held constant, again we can hand calculate the value of beta. It's the change of ln(r) over the change of ln(b). The physical meaning of this is just the slope of ln(r) versus ln(b). That's just the slope. But again, we can do the hand calculations as well. If you know the values of the reaction rate constants at two different concentrations of B, we're plugging all the numbers, we get beta. For example, if the reaction rate quadruples when B is doubled, then B2 over B1 is 2, R2 over R1 is 4. Plugging all those values, beta equals 2. The overall order of this reaction is alpha plus beta. And also, if we have the values of the reaction rate at three different combinations of concentrations of A and B, we can then write out three equations. And these three are linear equations. They contain three variables: K, the rate constants, alpha, and beta. We just need to plug in the values of R at different concentrations of A and B. And then we have three linear equations that contain three variables. In principle, we can solve the three equations and get the values of K, the rate constant, alpha and beta, the reaction orders, with respect to A and B. Now let's examine the zeroth order, first order, and second order reactions and derive their integrated rate laws. For the zeroth order reaction from A to P, the reaction rate is constant. R is simply equal to K, or K times A to the power of 0. Either way, K is the reaction rate constant. Sometimes it's called a reaction rate coefficient because scientists feel like this K may change with temperature. So maybe coefficient is a better naming for K. Now R is often defined to be dP over dt, how fast P is produced, or how fast the concentration of P changes with time. And looking at these two equations, we know dP over dt is K, so dP is K dt. We integrate both sides, and then we have P equals P naught plus KT. P naught is simply just P at time 0, so you can verify this equation. You plug in time equals 0, you get P equals P naught. That's it. Very often P naught is 0. You know, why would we have any product at the beginning of the reaction unless you put some product in the reaction system? and that's rare. So very often we have just P equals KT. But this is kind of more general equation. Now let's look at one numerical example problem, 12.3.1. In zeroth order reaction, the concentration of the product is 0.065 molar at 1 minute, 0.095 minute at 2 minutes. Determine the rate constant K and also P naught. So we have this equation. We plug in all the values. We solve this equation. We get K is 0.03 molar per minute. Well, it's really simple. You just take difference between these two equations. You'll get K. And then you plug in the value of K, you get P naught, which is 0.035 molar. So that means at the beginning of this reaction, we have some P already in the system. Its concentration is 0.035 molar. If we plot P versus time for the zeroth order reaction, it's just linear. And over here, the intercept is the initial concentration of the product. Well, usually this is 0. The slope is just a constant K at a given temperature. For the zeroth order reaction from A to P, the reaction rate is constant. We have P equals P naught plus KT. So we can make a graph of P versus time. The intercept is P naught, the slope is K. So we can always make a plot like this to determine the value of K if we have more than 2 data points. If we have only 2 data points, I'd rather just solve 2 linear equations. Again, if P naught is 0, then P is equal to KT. And this is actually more common. Why would a reaction be a zeroth order reaction? Why does the reaction rate R not depend on the concentration of the reactants? There are 3 possible reasons. One is we do have a reactant A, it's constantly consumed, but it's also constantly replenished, so that A never changes. A is kept constant. Alright, so there's one way to do it. Reason number 2, A is a pure liquid or pure solid, so the concentration of A is constant. For example, if the reactant is just pure water, pure water has a constant concentration in molar or mole or mole fraction. If you look at the mole fraction of pure water, it's always 1, so it never changes. Reason number 3, A decreases as the reaction proceeds, okay, but R does not depend on A. For example, if we have a reaction that's induced by photons, and only if A absorbs a photon, a reaction can take place, and we have fewer photons than the number of A's, and then the reaction rate solely depends on the number of photons provided to the system per unit time, right? So if you have, for example, a bunch of A but only 1 photon per hour, then the reaction rate is just 1 molecule of A converted per hour. It has nothing to do with the concentration of A anymore. It's limited by the number of photons provided to the system per unit time. Because A may be constant as the reaction proceeds, we don't usually like to use this equation to define the reaction rate R. What if A is always replenished, A is a pure liquid, and then dA is just 0, then R is 0, and that's not true. So very often we do not use this equation for the reaction rate. Instead, we say the reaction rate is equal to dP over dt for the zeroth order reactions. For the first order elementary reaction from A to P, R is K times A to the power 1. And now we can write the reaction rate as the consumption rate of A or the production rate of P at the same time. We have three equal signs, but we will use this equation to solve for the integrated law of the first order reactions, because if we look at this equation, there are only two variables: A changes, T changes. K is constant at a given temperature. So how do we solve this? First, we rearrange the variables. So A appears on one side of the equation, T appears on the other side. The separation of variables is very important. We do that first so that we can integrate both sides. Again, if you have two variables on the same side of the equation, you cannot easily integrate that side. You want to have only one variable on each side of the equation before you integrate both sides. The integral of dA over A is Ln(A), the integral of negative k dt is negative kt, and because we're doing indefinite integrals without lower and upper limits, we need to plus a constant. We can determine the constant C given the initial condition. If A is A naught when time is 0, and A naught denotes A at time 0, then we plug in those expressions. We replace A with A naught and T with 0, and you can see this constant C over here in this equation is simply ln A naught. Therefore, ln A is negative kt plus ln A naught. Equivalently, A is A naught times exponential function. This exponential function is e to the power of negative kt. And now, if you just look at these two equations, we can use either one to analyze this concentration change of A. If we use the logarithm equation, we can make a graph of ln A versus time. You can see the slope should be negative k, the intercept should be ln A naught. So this is one way to determine the reaction rate constant K. Just plot ln A versus T, you get a linear equation. The slope is negative K. And if you have only two data points, you can always solve two linear equations that contain two variables. Alright, so for example, if you know the concentration of A at the beginning and the concentration of A after 1 second, and it's the first order equation, so you can use this, and then you can hand calculate the value of K as well. You can also use this equation if you have the initial concentration of A, alright, and you have this, and at t equals 1 second or 2 minutes, whatever, you have another concentration of A. Plugging all those values, you determine K. So it's possible to hand calculate the value of K. But if you have more than 2 data points, if you have 3 data points, 4 data points at different time, just make a graph, do a linear regression, determine the slope, and remember the slope is negative K. I did use ln A as the vertical axis, but really it should be ln A over molar, just to remove the unit. It's just because the logarithm of a unit makes no sense. What's the logarithm of 1 molar? It just doesn't make any sense to have the logarithm of a unit. What's the logarithm of kilogram? It does not make sense. But just for convenience, I'm just using ln right here. You need to keep in mind that when you do this, you are actually removing the units. Now again, look at the rate expression. It can be the consumption rate of A, it can be the production rate of P. So we have negative dA over dt equals dP over dt. Therefore, the sum of these two should be 0. So we have this equation. That means A plus B never changes. Well, that makes sense because whenever one A molecule is consumed, one P molecule is produced. So A plus P never changes. Therefore, A plus P is always A naught plus P naught, and P is A naught plus P naught minus A. And because A is A naught times e to the power of negative kt, so P is P naught plus A naught times 1 minus e to the power of negative kt. Very often, the initial concentration of P is 0, which is again very common. It's rare for us to put some product in the reaction system in the first place. So usually we have P naught is 0, then P is A naught times 1 minus e to the power of negative kt. Alright, we have the expression for the concentration of P as well, and we can plot how P changes with time. Now let's look at the half-life of A. What's half-life? That's when the concentration of A drops to only 50% of the initial concentration. So based on this definition, well, the concentration at half-life is just 1/2 of A naught. And it's also equal to A naught times e to the power of negative k times half-life. So this is from the integrated rate law of the first order reaction. Now if we compare these two sides, we know we have this A drops to 1/2 of the initial concentration. This exponential function e to the power of k times the half-life should be 1/2. And now you have this equation, and then we solve this equation. Given k, we get half-life. Given half-life, we get k. Here's one numerical example problem. 12.3.2, in first order elementary reaction from A to P, the concentration of A is 0.2 molar at 1 minute, 0.14 molar at 2 minutes. Determine the half-life of A and determine the initial concentration of A. So we're going to use this equation, alright? Ln A equals negative kt plus, actually this Ln A naught. But we don't even need to know that equation, because we know negative k is going to be the slope of Ln A versus time. So we have the change of Ln A on top, the change of time on the bottom. We determine negative k, it's this. So k is 0.3567 per minute, or 0.005945 per second. Well, I'm keeping actually one extra 6 figures. I usually do that for intermediate results. Now half-life. Half-life is just ln2 over k. So plugging all the numbers, half-life is determined to be 116.6 seconds, or 1.943 minutes. Since we have this equation, so again, this C is actually Ln A naught. Now we just need to use this equation. We're plugging all the numbers. We can use the data at 1 minute or the data at 2 minutes. It doesn't matter. We just plug in the corresponding concentration of A. 0.14 at 2 minutes, 0.2 at 1 minute. We plug in the K with the right unit. Alright, so we're going to use per minute over here, so 2 minutes over here. We determine the concentration of A naught, which is 0.286 molar. Actually, you can just compare 0.286 and 0.14. Well, you can see roughly 0.14 is 1/2 of the initial concentration, so 2 minutes should be close to the half-life. And yes, 2 minutes is indeed close to the half-life. Now let's look at the second order reaction from 2A to P. First, R is K times A squared. That's the rate law for the second order reactions. We need to determine the integrated rate law and half-life. So we write out the reaction rate as how fast the product changes with time. But look, when one product P is produced, 2A are consumed. So the consumption rate of A is 2 times the production rate of P. So this dA over dt is 2 times this dP over dt. That's why we need to put a 1/2 here to balance this equation. We put a negative sign here because dA over dt is negative. dP over dt is positive. So it makes sense to put a negative sign. Or we can say the absolute value of this. But mathematically, it's better to use the negative sign here. Now we just need to solve this equation. How do we solve this? Again, there are 2 variables. We have the concentration of A, we have time t. Always separate the variables. By doing some simple algebraic operations, we managed to have A on the left hand side, t on the right hand side. And then we can integrate both sides. The integral of the left hand side is 1 over A. The integral of the right side is 2kt. But both are indefinite integrals. So we're going to just write plus c, and c is a constant. We can determine the value of the expression of c given the initial concentration of A at time 0. You just plug in A being A0 here, T being 0 here, and then we can solve for C. Alright, so what is C? C is simply just 1 over A naught. And therefore we get this equation as the integrated law for the second order reaction from 2A to P. It's 1 over A equals 1 over A naught plus 2kt. By looking at this equation, we know if we plot 1 over A versus time, we'll get a slope, and the slope is 2k. The y-intercept is going to be 1 over A naught. Again, for the second order reaction from 2A to P, the reaction rate is 1/2 of dA over dt, and it's dP over dt. And therefore you can see 1/2 dA over dt plus dP over dt should be 0. Therefore we have this equal to 0, and A over 2 plus P is a constant. It never changes with time. Only because when 2A molecules are consumed, 1P is generated. Right? So we have this equation. A over 2 plus P is equal to its value at the beginning. It never changes. And using this equation, we know P is P naught plus 1/2 of A naught minus A. This is the change of A divided by 2. That will be the change of P. If the initial concentration of P is 0, which is common, P naught is 0, then P is just 1/2 of A naught minus A. The half-life of A can be calculated easily using this equation from the integrated rate law. It's just we need to use the equation for the time right at the half-life of A. Therefore 1 over the concentration of A at half-life is 1 over A naught over 2. That's the definition of half-life. It's equal to 1 over A naught plus 2k times half-life. That's from the integrated rate law. Now we can solve this equation really easily. So we have 2 over A naught, which is from here, minus 1 over A naught is 2k times half-life. It's kind of interesting here. The half-life of the reactant in the second order elementary reaction depends not only on the rate constant but also on the initial concentration of the reactant. Because by looking at this, you know the half-life is 1 over 2k times A naught. It depends on both k and A naught. Recall that for the first order reaction from A to P, the half-life is ln2 over k. The half-life of the first order reaction depends only on the value of the rate constant. But over here, the second order, this half-life depends on both k and A naught. Now let's look at one numerical example problem, 12.3.3. In a second order elementary reaction from 2A to P, we have some data points. A is 0.2 molar at 1 minute, 0.14 molar at 2 minutes. Determine the rate constant, determine the initial concentration of A, and also the half-life of A. We first write out this equation. We realize that if we plot 1 over A versus T, we'll get 2K. So 2K is the slope of 1 over A versus time. So 2K is the change of 1 over A divided by the change of time. We plug in all the values. We get the expression of 2K. 2K is 2.143 molar to the power of -1, minute to the power of -1. And therefore K is 1/2 of this. And then this value divided by 60, we get the value of K in molar -1, second -1. Again, we have this equation. We can just plug in the values of A at 1 minute. So this is concentration of A. This is 1 minute. We solve for A naught. We got A naught equals to 0.35 molar. And how do we get a half-life? Well, the half-life is 1 over 2K A naught. We plug in the value of K, the value of A naught. We get 1.333 minute, 80 seconds. So after 80 seconds, the concentration of A is 1/2 of this, and that's 0.175 molar, which is between these two concentrations given in the question. And also you can see this 80 seconds is between 1 minute and 2 minutes. It's a good way to quickly verify if our answer makes sense. There's another type of second order reactions from A plus B to P. In this case, if A equals B, so if we use the same amount for A and B, then we have this equation. R is K times A times B, but since A equals B, so it's A Ka squared or Kb squared, either way. And the consumption rate is this, and this, and this is the production rate. Note that we do not have 1/2 in front of dA over dt, because look at this coefficient, it's 1-to-1 ratio. And now we just solve this differential equation. It comes from over here, Ka squared equals negative dA over dt, and then we have this equation. We integrate both sides, we get this. 1 over A is 1 over A naught plus KT, and A naught is A at time 0. Alright, we can just easily verify this. We can plug in this expression here, dA over A squared, just to see if it equals kdt, or we can plug it in here, negative dA over t, right? See if that's K squared. We can verify this equation easily. And now we have this equation. If 1A is consumed, then 1P is produced. So we have this equation. Oh, by the way, if 1A is consumed, at the same time 1B is also consumed, and 1P is produced. So we got this equation, and you can see A plus B never changes. Therefore, A plus P is A naught plus P naught. P naught is often 0. But what if P naught is not 0? Then P is P naught plus A naught minus A. If P naught is 0, then P is A naught minus A. The half-life of A can be calculated using this. Again, this is going to be just 1 over the concentration of A at half-life, which is 1/2 of the initial concentration, which equals this, and then we get the half-life. This half-life is 1 over K A naught. It's a little different from the half-life of A for the second order reaction from 2A to P. So I'm going to show you that half-life. it's 1 over 2k a naught. Here it's 1 over k a naught. Again, it's just because if you look at this equation, 1a, 1p. In the previous equation, it's 2a, 1p. Let's look at a numerical example problem in a second order elementary reaction from a plus b to p. We have concentration of A at 1 minute and its concentration at 2 minutes. Now this time we're going to solve everything using a slightly different equation. It's just 1 over A equals 1 over A naught plus KT, and K is the slope of 1 over A versus T. So I'm going to use the change of 1 over A on top, the change of T on the bottom. We get the value of K, and we can convert minute to second easily. We write out this equation. Again, we plug in the value of the concentration of A at 1 minute. We can solve for A naught. In this case, A naught is also 0.35 molar. The half-life is 1 over K times A naught, and this time we have 1 over K A naught. It's just the same value, 80 seconds. So in this numerical example, we got the same initial concentration, same half-life, but this K is different. Over here we get K 2.1. I want to show you the previous calculation. This 2K is 2.1. Alright, 1K is 1.07. So the value of K is different between these two examples, but A naught is 0.35 in both examples. Half-life is 80 seconds. Half-life is 80 seconds. Initial concentration is 0.35. For the second order reaction from A plus B to P, it's possible for A to be different from B. That makes the derivation more complicated. We'll just assume B is always A plus delta, because dA over dt equals dB over dt. Given a time period, the change of A should be equal to the change of B. Then we have this equation. That means the change over here of B with respect to time is equal to the change of A with respect to time. Alright, so B minus A never changes. If B minus A never changes, then this delta is a constant. Delta never changes with time. So if at the beginning you have delta equals B naught minus A naught, then throughout the entire reaction, delta is B naught minus A naught. No change. And now R is Ka times B. B is A plus delta. And it's equal to the consumption rate of A or B or the production rate of P. We will solve this equation because it contains only two variables, A and T. We do need to separate the variables again, so we have K times dt equals negative dA over A, and also we have A plus delta on the bottom. How do we integrate this by hand? Well, it's just we can separate this two. We get this expression. So I'll let you verify the left side of the equal sign equals the right side. Alright, we can now integrate both sides. That's easy. KT is just 1 over delta times the integral of this, which is the logarithm, minus 1 over delta times the logarithm of this, which is normal, which is easy. Got this equation. I did take the initial condition into account, because really if you integrate both sides directly, you're going to get indefinite integrals. But we do know that at time 0, A is A naught. So I'm using this equation to get a definite equation. We can verify this easily. When time is 0, the left side is 0. And when time is 0, A is A naught. A is A naught. The right side is 0. So that's good. Now we have this equation. So again, the difference between two logarithms can be expressed of the logarithm of a division. So over here, and now we can calculate the half-life of A. We just need to replace A with 1/2 of A naught. So that's what I did here. A is 1/2 of A naught. Alright, A is 1/2 of A naught. So this is just 1/2 on the bottom. That means you have a 2 on top. Get this equation, and you simplify everything, you get this equation. The half-life in this case, the half-life of A in this case is just this 1 over delta times Ln A naught plus 2 delta A naught plus delta. What's the half-life of B? Well, it's similar. You just need to replace A naught with B naught. You get the half-life of B. It's really easy. Alright, although it's in the expression of a logarithm of a ratio between A naught plus 2 delta over A naught plus delta. What if delta approaches 0? How do we deal with this? When delta approaches 0, actually we need to know a little bit about Taylor expansion. So this approaches this. If you know how to do Taylor expansion, the Taylor expansion tells us the logarithm of 1 plus delta is roughly delta, if delta is small. So over here we can see this term is roughly 1 plus, when I say delta, that means a very small number. So not this delta. So the logarithm of let's say 1 plus x is approximately x, if x is really small. Alright, if x is really close to 0, let's say if x is 0.01, then the logarithm of 1.01 is roughly 0.001. That's just from the Taylor expansion of the logarithm. Okay, let's get back to this. This part is just 1 plus delta over A naught plus delta. So roughly the logarithm is delta over A naught plus delta. And over here we have 1 over delta, so this whole thing is roughly 1 over A naught plus delta. And this is roughly 1 over A naught. Alright, so when delta approaches 0, we have this equation. And K times half-life is roughly 1 over A naught. And isn't that just the half-life here? The half-life is 1 over K A naught. Get back to this. When delta approaches 0, what's the half-life? Half-life is 1 over K A naught. You know, same thing. Alright, when delta approaches 0, we just reduced the more complex situation to over here. I'm sorry, on this page, you know, when A is equal to B, the half-life is 1 over K A naught. And over here, same thing. When delta is approaching 0, K half-life is 1 over A naught. Therefore, half-life is 1 over K A naught. Alright, so in this case, you know, when delta is approaching 0, that means when B is approaching A, the half-life approaches 1 over K A naught. When B is equal to A, the half-life is equal to 1 over K A naught. The last slide of this section, briefly I'll talk about the third order only because I want to show you it's possible to deal with the third order, the fourth order, etc. This is the third order. RSK times a to the power of 3, and it's negative 1/3 dA over dt equals dP over dt. We just solve this differential equation. We separate the variables, a on the left hand side, t on the right hand side. We integrate both sides. We get 1 over 2a squared plus 3kt plus a constant. Alright, and then we can determine the expression of the constant because we know at time 0 a is a naught. Plug in a naught here, plug in t is 0 here, c is 1 over 2a naught squared. And now we have the third order rate law, which is 1 over a squared is equal to 6kt plus 1 over a naught squared. We make a graph. It's 1 over a squared. Over here it's t. The slope is 6k. The intercept is 1 over a naught squared. That's it. So given the experimental data, we'll just be able to create a graph and determine the slope. The slope divided by 6 is going to be the rate constant. Also, if you have the concentration of A at 2 different times, plug in those values, we can just solve for K and solve for A naught easily.